Okay, so the next talk today is by Matt Hogancamp on curved Hecke categories 3.
Great. Well, thank you for the introduction and for the invitation and organizing and putting together everything in the presence of COVID. Today I'll be talking about, so the first talk of this morning was Shotaro Makisumi. We all just call him Maki though. He was talking about so his talk was the curved Hecke categories 1 and 2. And in this talk, I'll talk about a sort of third paper that we're working on, which is a generalization to arbitrary types of something that was done in type A by me and Eugene Gorsky. So throughout this talk, we will have a conjectured group. So W will always just be a conjectured group. Its set of simple reflections will be denoted by S in the usual way. And we'll have to pick a realization of the conjectured group. So for now, you should just think of the realization as being a particular kind of finite dimensional representation. And the one example to have in mind, the type A example, is the case where your conjectured group is just a symmetric group. The set of simple reflections is just the usual set of simple transpositions, swapping I and his neighbor. And H, there's different things you could choose for the realization. For example, you could take the n-dimensional realization on which Sn acts by just permuting coordinates. So this is the basic input. And the goal of today's talk is, the goal of today's talk is to understand this diagram of categories and functors. Okay, so I've kind of color-coded everything. So this notation is slightly different than what we saw in Maki's talk, but let me explain the various pieces, or summarize the various pieces. So here we have something which is familiar to many people here. It will be denoted by BE. This is the usual homotopy category of complexes of Zergle bimodules. So the B and the E stand for bi-equivariance. This is, the name is inspired from the geometric construction of this category. Down here, we have the left monodromic category. So these are like, this is a version of complexes over Zergle modules. So you take here the left quotient of Zergle bimodules, and we're looking at the homotopy category of complexes in that category. This FM for the free monodromic category is the Koszul dual of BE. This is the guy that was talked about. So Maki talked about this in his talk. So in that talk, it would have been denoted. So this would have been D mix of, let's see if I can get it right. So this would be G mod U mod U. And this would be, down here would be D mix of G U mod U mod B. So that's this notation. Okay, so far these three categories down below are familiar to us. And one of the primary goals of this talk, we won't get to it until part 2 most likely, but the primary goals of this talk is to introduce this category up here, this guy Y, which is what I'm going to refer to as the curved Hecke category. And the Koszul duality, let me just, I won't write this here, but the Koszul duality statement is, so Koszul duality exchanges this guy with the Langlands dual, swaps these two, the green and blue categories for the Langlands dual. So swaps this guy for H with the FM for H dual, and vice versa. And the sort of conjecture, which is pretty enticing, is that this guy also has the same sort of Koszul self-duality properties as the category O, as the LM category. Okay. So anyway, so the goal of the talk is to kind of understand these categories in their relationship with one another, primarily this yellow guy up top. Now the motivation, the original motivation for this was, in type A anyway, was this conjecture of Gorsky, Nagus, Rasmussen. So this conjecture, which is actually maybe not quite correct as stated, but this is a kind of a version of a conjecture in Gorsky, Nagus, Rasmussen. So there should be a functor from the categories. Remember, this is the homotopy category of complexes of Zergle bimodules, and there should be a functor which sends such a complex to a sheaf on the Hilbert scheme of points in C2. So that there's many properties one expects of such a functor, but one such property is that this diagram commutes. So you have a functor from sheaves in the Hilbert scheme to vector spaces, which it just takes global sections. And then you have a functor from Zergle bimodules to vector spaces, which just computes Hams from the identity object. And then the conjecture is that there is a functor relating these two categories, making this triangle commute. But notice there's some incompatibilities here. Let me just point out that the cohomology of a sheaf on the Hilbert scheme, sorry, this is kind of wonky. Okay, so the cohomology of a sheaf on the Hilbert scheme is automatically a module. So this is just a vector space, but it's more than just a vector space. It's a module over global functions on the Hilbert scheme. So global functions on the Hilbert scheme is this ring of symmetric polynomials. So you have polynomials in two sets of n variables, and you're looking at functions which are sort of which are invariant under the diagonal as n action. So this guy acts on the cohomology of any sheaf. So in particular, if this conjecture were true, you would expect that ring to act on Hams from the identity into that object X. But here you see a mismatch. The Hams from the identity object into a Zergle bimodule, or a complex of Zergle bimodules X, is a module over this this other guy. The endomorphism ring of the identity here is just a polynomial ring in n variables X. You should ignore the fact that there's a symmetry group invariance that we're taking here is kind of inessential. It can be kind of dealt with. The more serious problem is that there are no variables y that act on a complex of Zergle bimodules, or rather this Hom space. So the more serious issue is the lack of y's, and the problem that this category curly y was designed to solve is the problem is that so the interaction of this category was designed to replace the category of Zergle bimodules in this conjecture. Sorry. So you get a more sensible looking statement. So you get a more sensible looking statement. So this BE should really be sort of replaced by Y. There's two ways of fixing this funny mismatch of the left and right hand side. One way is to restrict the right hand side to sheaves supported on the x-axis. And the other way is to sort of enhance the left-hand side to include things away from the x-axis, roughly speaking. Okay, so this is all just motivation. Okay. So I will define this category Y in arbitrary types, but the sort of motivating, anyway, so the motivating problem was to have a version of the category Zergle bimodules which has basically a symmetry which the original category of Zergle bimodules did not have. All right, so this talk will be basically in 4 parts, one for each of the 4 categories. So the first part, I just want to recall the definition of Zergle bimodules in this so-called bi-equivariant category. Okay, so this will be pretty standard and probably familiar to many people here. So I would like to introduce the category Zergle bimodules first. So remember, we have this realization of our Koszul group. The realization is called H. So we define a polynomial ring. So we define R to be the symmetric algebra of H dual. In other words, this is the ring of polynomial functions on H, whatever. So we can write it as after choosing a basis of H dual, we can write R as the polynomial ring in these generators. And we'll regard this as a graded ring by declaring that every linear polynomial lives in degree 2. So SBIM, the category of Zergle bimodules, depending on the Koszul group and its realization, is just it is a subcategory of graded bimodules over this ring. And it's the subcategory generated by bimodules of this form. So these are called Bott-Samuelson bimodules. They're just tensor products of copies of R. And then the intermediate rings are these guys, RS, RT, RU, where T and U, S, T, U are simple reflections. So the notation here just means, so RS, so if S is a simple reflection, R upper S is just the set of polynomials which are S invariant. Okay, so you look at all bimodules which can be expressed as direct sums of direct summands of shifts of bimodules like that. And this is the category of Zergle bimodules. Let me emphasize that here I don't want to worry about the ground ring at all, so everything is over the complex numbers. But everything that I say can be, you can still make sense of it for arbitrary, well, for more general rings of scalars. Okay. So the category BE then is just defined to be the homotopy category of complexes of Zergle bimodules. Okay, just to make some quick observations, SBIM is monoidal. So it's closed under the tensor product. I'll just denote this by a star. It's closed under the tensor product over R. And there's an identity bimodule. So the monoidal identity is just the trivial bimodule. So this guy is a monoidal category. And because SBIM is monoidal, its category of complexes is also monoidal. Just by the usual formulas. If you know how to tensor objects of a category, then you also know how to tensor complexes of objects in that category. Okay. So next I want to describe the LM category. So again, this will be something of review. So the LM category, to warm up, I want to consider the left quotient of SBIM. So I'll denote this by the tensor product. So this is just notation that indicates what's happening here. So objects of this category, of this left quotient, are just, you take Zergle bimodules. So you take Zergle bimodule B, and you kill the left action of positive degree polynomials. So you tensor on the left with the trivial R module. So this has the effect of killing everything on the left, and you regard the resulting thing as just a right R module. In fact, a graded right R module. So, and morphisms in this category are just bimodule maps. So sometimes this category is called just Zergle modules. And this is the category that's very closely related to a graded version of category O. So I won't write this, but if your Koszul group is a Weil group, then this category is essentially, or up to taking the right categories, this is the category O of the associated Lie algebra. Okay, graded category O. So what you want to do for LM is you would like to not sort of kill the action of positive degree polynomials on the left. You don't want to kill it sort of forcefully. You want to kill it gently by adjoining some odd variables whose differentials are the x's. So there's a sort of homotopy theoretic way of performing this quotient that gives you the actual category LM. So for this, we need a little bit of notation. So this is, again, similar to what was said in Mackey's talk. I would like to define an algebra. So K will be the polynomial ring. You adjoin some odd variable. So my notation for this is going to be the same as that for a polynomial ring. So these thetas are meant to be odd variables, so which means they square to 0 and the anti-commute. And I'll declare that they're differentials. So this is really a DG algebra over R. I'll declare that D of theta I is xi. And just for the sake of, I don't want to confuse everyone by talking about gradings, but let me just write that everything here should be regarded as bi-graded. So the degree of xi, the cohomological degree of xi is 0. And the other degree, the sort of Zergle degree of xi is 2. So I'm going to write degrees multiplicatively in this way. So t to the 0 means it has cohomological degree 0. Q squared means it has q degree 2. And the theta i's will have degrees. They'll have cohomological degree -1 because they're like homotopies, and q degree 2 because they kill. Anyway, so this guarantees that the differential has degree 1. Okay. If you like everything to be written in a basis independent way, then you could write this as the symmetric algebra of H dual tensored with the exterior algebra of H dual with the appropriate gradings inserted. But I much prefer to have bases around and explicit formulas like this. Okay, so that's our guy K. And so notice these, so this is the Koszul complex that resolves the trivial module, the trivial R module as a free R module. So anyway, the LM category is the category see how I want to write this. So LM is the category whose objects, so I'll describe objects of this category, and morphisms will be hopefully obvious at the point. So whose objects are complexes of the following form. So all of the chain, well, I'll write it, okay, so the underlying chain groups or whatever of this complex look like our Koszul complex K tensored with a Zergle bimodule. And from here on out, the realization and the Koszul group will be sort of understood. Or sorry, the Koszul group and the realization will be understood, so I'm going to omit them from the notation. And we allow complexes, so we allow complexes of this form, but the differential, so notice K itself is a chain complex, and we allow components of our differential that map between different parts of the complex. So you're used to your differentials mapping just between adjacent terms, but now the chain groups themselves have some sort of like internal cohomological degree. So you can actually have long parts of your differential that involve the internal degree in K as well. So this is known as a twisted complex. Anyway, so the LM is the category whose objects are complexes like this, where the differential is required to be K-linear. Okay, and then the morphisms are morphisms in the category of Zergle complexes of Zergle bimodules, which are also K equivariant. So everything in sight has an action of K on the left by construction, and we require all of our morphisms to be not only bilinear with respect to the RR action, but also linear with respect to the K action. And I think probably an example will clear up any potential questions. So I'll state an example and then we'll have our break. So the following is a chain complex in the left quotient. Sorry. So this is going to be rank 1. So if our Koszul group has just one simple reflection and the identity element, we choose the realization which is one-dimensional. Oops. Then we have a chain complex that looks like you have 3 bimodules, and there's a map that's from R, so where B is the bimodule R tensor R over RS. So you have a chain map, or you have a bimodule map from R to B that sends 1 into this simple tensor, or this tensor. Then you have a bimodule map from B into R that sends 1 tensor 1 to 1. And you notice this does not define a chain complex. Oops, sorry. Thank you, Ben. So notice this doesn't define a chain complex because D squared sends 1 in the leftmost position to a 2x in the rightmost position. Okay, but this is 0 in the left quotient. Now I'm claiming that the category LM is a sort of homotopy friendly way of performing this left quotient. And so what does that mean? That means you take the complex, the sort of non-complex that you wrote at the previous step, and now you tensor everything with the Koszul guy, K. And then you say, well, d squared is now not equal to 0, but it's homotopic to 0. D squared was something living in, it was a positive degree polynomial acting on the left, and such things are killed by tensoring with K. So there's an extra term you can add to the differential that makes the sort of total complex here actually a complex, and this defines an object inside LM. And it may concern you that now our differentials are long, but look, this differential looks like it has degree 2 because it's mapping from something in degree 0 to something in degree 2. But that's compensated for by the fact that it actually has sort of an eternal degree -1 relative to K. So in the end, everything is actually homogeneous with respect to some total degree on these complexes. And I think I'll stop there and take questions.
Great. We'll reconvene the true lecture at 10:32. And questions.
So I see some questions in the chat, but were they answered?
I mean, maybe I can ask it again. So the twisted complex you wrote over there, you don't constrain the parity on the length of the long differential, right? Could be...
No. At this point, no.
Yeah, sorry, I was muted. So the fact that you tensor with K and you do this construction and you get equivalent to naive LM is because everything was free on the left over R?
Yeah, you use that. All Hom spaces are free over R. That's right, in the Zergle category.
May I ask you?
Yes.
I'm a little bit confused. So up to the last move, it seemed that you applied Koszul duality to left variables. You traded them for odd variables. Am I right?
Yes. Yeah.
But your final, which means that you still have an equivalent category to bimodules, to how do you call them, bi-equivariant ones. You just traded.
No, the left variables are still there.
So you didn't really, okay.
Oh, you don't forget, didn't you forget them when you introduce your thetas?
Well, they're now null homotopic.
He just derived restriction. So I mean, he doesn't want to kill the variables. He just wants to kill them in derived way. That's exactly what it's our paper.
But that's the way. But that's the way to describe Koszul duality when you trade one even variable for one odd variable.
No, it's not Koszul duality. That's derived restriction. That's what it
does. So I don't know if I'm going to answer your question, Lev, but there's something that I wanted to say before the break that I didn't quite get to, which is Hom spaces in BE.
Mm-hmm.
And I think it's important to ask questions like this. Hom spaces in BE are modules over, well, you have a left action of R and a right action of R.
Mm-hmm.
Okay, Hom spaces in LM, what did we do? Well, we killed R, right? We killed the left R, right?
Yes.
But in doing so, somehow we pick up an action of R check, where R check is the following object. R check is polynomial ring in these Y's. where y's are dual to x's.
Oh, I think I understand what you did. So I had a misunderstanding initially. So you're
Yes,
not
I think that if you keep this in mind, I'm not regarding everything. I mean, I am kind of regarding. Yeah, I mean, I'm doing something different than just trading the left
yes.
r for a lambda. I'm trading the left r for an r check somehow.
Oh, yes. So if I may say how I understand it right now. So you say that in addition to left variables x, you introduce a brand new set of n variables y, which is equivalent to introducing brand new set of variables theta. You just introduce them. And then you introduce a superpotential sum of xi, yi on the left.
You're describing, I think you're about to describe the category FM.
Yes, which would be equivalent to adding the differential in the theta language.
Let me.
Okay.
So this can be horribly confusing for everyone, especially if this is new, and you're learning this for the first time.
Can I say something to
so
It's time to continue, so you can continue now.
It's time to continue. Lev, I expect we'll talk at length about this after the talk, so stick around. But let me just say for now, to kind of continue the question that was asked, or the answer that was started a second ago. Something kind of funny happened. So that one reason why LM is better in some sense than just the left quotient is because it makes obvious this extra action of R check. And I want to spend just a second talking about this left action of R check. So where does it come from? This will be somewhat self-contained. But I think it's a useful little mini lesson. So consider like this is now kind of somewhat abstract situation. If you have any algebra over a ring R, then HH upper 0, this Hochschild cohomology, is just a fancy word for the center of A. And the center of A is slightly, is also, can be thought of as the center of the category of A modules. In other words, the center of A acts naturally on any module. Any module you can left multiply by a central. Oh, sorry, thank you. The higher Hochschild cohomologies of A also have such an interpretation. These now act not on an object of A mod, but on objects of the derived category of A mod. So Hochschild cohomology, for example, HH upper 1 is generated by derivations of your algebra A. And the way you should think about this is that if you have a complex of A modules, or like free A modules, its differential is represented by a bunch of matrices. Coefficients of those matrices are elements of A. And you just pair your class in Hochschild cohomology against your entries of the matrix to get your entomorphism. So by taking a derivation of the differential, you get an entomorphism of a complex. Okay? And that's the sort of thing that's happening here for this R check action. So the observation is that if you think of K as being an algebra over R, then when you compute its Hochschild homology, this is an exercise for those who are interested. Its Hochschild homology is in fact this guy R check. So if you have like a complex of K modules or a DG K module, R check will just naturally act on it. And that's where this is the monodromy action. In the word left monodromic, this is the sort of titular monodromy action. Okay, just in case you were curious. So this is, that's all I want to say about BE and LM for now. So BE has a couple of R's, LM has an R and an R check. And so next, I want to introduce this category Y. So we'll spend a significant amount of time talking about this guy. Okay, so recall, we have these algebras R, K. Well, we won't really need K for now, but we also have R check. So I'd like to define for each pair of elements in the Koszul group, I'd like to define a category Y sub VW as follows. So objects of this category are going to be pairs. I'll call it X comma nabla, where X is a complex of Zergle bimodules, and nabla is an endomorphism of degree 1. Well, so I want to write things in this way. So we take the endomorphism, the complex of endomorphisms of X. This is a bi-graded type of object because X is a complex of graded bimodules. So nabla is a differential, which means it has degree, cohomological degree 1 and Q degree 0. I also require, oh, sorry, it's not living in the endomorphism algebra of X. I want to adjoin a copy of R check. So you should think of this as just an extension of scalars. I just take the endomorphism algebra and now I allow coefficients to include polynomials in Y. So I require that this differential agrees with the given differential on X, mod Y's. And d squared is actually not 0. D squared is instead an expression that looks like this. So we take the fixed element W evaluated on xi upper L. So the superscript L denotes the operation of left multiplication by xi. Similarly, xi upper R denotes the action of right multiplication by xi. Okay, and I require that delta squared is this funny non-zero expression. And morphisms in this category are just, so if you have two complexes of Zergle bimodules, you look at the complex of Homs from X to Y. If each X and Y comes with a sort of a nabla, like this differential with t squared not equal to 0, then we look at chain maps with respect to these funny differentials. So morphisms in this category are versions of chain maps. And we regard all these things modulo homotopy, where homotopy is defined in the usual sense with these new nabla differentials. And I suppose if I'm being precise, I probably, there's a question of whether or not let me just allow an arbitrary degree morphisms for now. Oops. Okay, so this is the category Y. And
Eugene is saying that the Hom space there should have a tensor R check with it.
You're right, I'm sorry. Goodness. You want to join our check to all Hom spaces here. Okay, and so in nice examples, so let me just explain what it means to be an object of this category. So in nice examples, nabla is in fact at worst linear and wise. So that means nabla can be written as the original differential on your object x plus some expression of this form. And just to remind you, these CIs are endomorphisms really of the complex x. And then the equation that nabla squared is what we want it to be. Xi on the left, or W of Xi minus on the left minus V of Xi on the right. This equation is equivalent to the statement that each one of these CIs is a homotopy for that expression, and the CI is anti-commute and squared is 0. Okay, so basically the data of an object in this case is equivalent to a collection of homotopies which kill action of polynomials on the left and on the right, twisted by the fixed elements V and W. Okay, and finally, the category. Oh, sorry. There's one more thing I want to observe, which is that there's a tensor product here. So the tensor product of complexes of Zergle bimodules gives rise to a kind of a convolution product here. So if the input is a complex of Zergle bimodules X with curved differential, and a complex of Zergle bimodules Y with some other curved differential, then the output is, well, you just tensor the complexes of Zergle bimodules, and then you do the sort of natural thing. You, this is the usual sort of formula for the tensor product differential. And this has the correct curvature. Okay, so there's a convolution product defined on these Y categories. So there's a special one of these guys that we prefer, which is the case where both V and W are 1. So it does just, whenever I write Y without decorations, I'll always just mean the category where both permutations are 1. So this is actually a monoidal category. So it's monoidal. It's a triangulated category, so it's the homotopy category of a pre-triangulated DG category, if you like to think about that kind of thing. So there's mapping cones, because anyway, even though these are not categories of complexes, they're categories of curved complexes, and all of the constructions that you know and love still make sense, like mapping cones and you know, shifts, direct sums, and all this kind of stuff. Still makes sense for these categories Y. Okay, so I want to talk about Hecke complexes just as a main example of this, and then I'll finish with just the relationship with the FM category at the end. So Okay, so if S is a simple reflection, we have the complex delta S, which I'll write in this way. So we have BS maps into the identity bimodule. And I'm kind of going to be ignoring grading shifts for the most part today. But if I were to not ignore grading shifts, I might put a grading shift here, where BS is notation for this bimodule, as usual. So that's the usual complex of Zergle bimodules associated to the simple simple reflection S. So this is living inside BE. What we want to do in this example is to understand how this object gets lifted to an object of Y. So it'll have the same chain groups, chain bimodules, and the differential on this lifted object will be the old differential plus some terms which are have degree 1 or higher in the Y variables. So what this looks like in practice is there's some backwards maps here. So this is the usual differential, which in the sort of Elias Williamson calculus is written as the sort of lollipop. And the backwards differential is a sum of so what I'd like to understand is there's some coefficients here. Times the backwards lollipop. And so if you notice, this differential, when we construct it, is actually linear in Y's. So the data of this delta tilde is exactly the data of a bunch of anti-commuting homotopies that kill the action of polynomials on the left and on the right. And this is an object not of Y11, but an object of YS1. And so to build it, what we recall, and I know I haven't really introduced the Elias Williamson calculus, but if you allow me some shorthand, so in the Elias Williamson graphical calculus, we have these relations that say the action of a polynomial on the left of this bimodule BS is equal to the action of S of that polynomial. Sorry, let me write it this way actually. So let me say it this way. The action of a polynomial on the right is equal to the action of the polynomial on the left, twisted by the simple transposition, plus this de Maistre operator applied to that polynomial. So by definition, this partial S of xi is defined by this equation. So it's the de Maistre operator applied to xi. Anyway, and so this equation implies, so if you take the standard Riquier complex for S, the following diagram defines a homotopy. So I'll take negative partial S of xi times the inverse lollipop. And the differential of this homotopy is exactly S of xi on the left minus xi on the right. Okay. So adding up these homotopies with coefficients gives us exactly, gives us exactly the sort of curved Rukia complex. We have the standard part of the differential pointing this way, and this guy pointing the other way. That is our curved lift of the standard Rukia complex, okay? So if you understand this example completely, then you pretty much understand the whole category. Every object of this category just looks like this. You take a complex of Zergle bimodules and you insert some backwards pointing arrows weighted by y's, so that d squared of this sort of deformed differential is this non-zero expression. It's the sum of y's times differences of x's. And the reason why this, so again, the backwards arrow could bother you here, but remember, y has cohomological degree 2. So this backwards arrow appears to have degree -1, but that's compensated by the cohomological degree of y. So in the end, you get a differential which is really homogeneous of the correct degree after you account for the degree, after you account for the degree of y here. Okay. So I'm about ready to discuss how to obtain FM from this category. But before I do, let me just remark. So y is monoidal. With the endomorphism ring of the identity being R check times R. And in fact, the left and right actions of this algebra coincide on every object. So this coincide on all objects in this category. So in other words, Hom spaces in Y are modules over R check tensor Y, or R check tensor R. Okay. And finally, the category FM can be obtained from this category Y by a similar procedure. So what I want to just kind of emphasize here is that the procedure by which, so we have these categories here. So BE, LM is something like, obtained from Zergle bimodules by introducing this Koszul complex K. And I just want to emphasize that the category FM is obtained from Y by a similar process. So for example, there is a functor from BE to LM with just tensors with K. And there is a functor from Y to FM once we define that, which tensors with K as well. So we'll obtain the definition of FM by a similar procedure. So definition, I'm going to call this FM prime because it's not, the definition doesn't sort of obviously coincide with the one in the literature. So I'll call it FM prime for now. This is the category whose objects are sort of objects in Y of the form so remember, an object of Y previously was just an object with a curved differential, but now we want our objects to be a particular form. We want them to, in fact, be K times some complex of Zergle bimodules. So this is a little bit imprecise, but I just want to, I want to emphasize that this guy has some differential already internal to it. And really the curve differential that we're considering is that plus some extra term. So this might be a little slightly more appropriate way of expressing these things. So you take the differential, which is internal to K, and you add to it these extra terms. Okay, so I don't know if I have time to really, so in practice, what this means is you take a complex of Zergle bimodules. For example, in rank 1, we have this complex of Zergle bimodules. From the previous example. Again, I'm omitting all the grading shifts here. So we really have a complex of Zergle bimodules like this. And I'm asserting that there's some way of inserting backwards arrow into this backwards arrows into this picture. So that the total differential of this guy, the square of it, is really non-zero. It's this difference of y's weighted by, or difference of x's weighted by y. And I think I will stop there. And just if there are questions about this, I can answer them later. Okay, thank you.
Very nice. Let me undo the spotlight so that we can see everyone. I have a question. So this complex that you just wrote down here, this tilting complex, this is in Y1, it's not in YS, it's like,
This guy is
take
in
Y1 and you get the free monodromic.
This one is in Y1, yes. This guy's in Y1.
Matt, would you mind if I made a quick observation?
Yes. No, I wouldn't mind.
Yeah, I'm a topologist, and I'd like to think of your construction in terms of topology. And I just wanted to make an observation, and I wonder if you could just verify it or just toss it out of the window. So I take a Zergle bimodules. I'm thinking of your category LM. I'm trying to think of how I should think of objects in your category LM.
LM?
So, yes, LM. So,
okay.
So say I have a Zergle bimodule, and let's say it's of Bot-Samuelson type. So as a topologist, I would that guy as the cohomology of the Bot-Samuelson variety, the equivariant cohomology of the Bot-Samuelson variety.
Okay.
So that's how one thinks of these Bot-Samuelson Zergle bimodules as a T equivariant cohomology. And so in the simplest case, it's the T equivariant cohomology of GI mod T. Right? And from what you were telling me, your objects in this LM are simply non-equivariant cohomology of GI mod. Just forget the equivariance, and you get a space that's just the Bot-Samuelson variety where you've forgotten the T equivariance, and that object is an object of LM. It still admits a map to BT because it's a principal T bundle on the right, and so you have a right BT action on it, but since you've forgotten the equivariance, there's no left action, or you've resolved the right action.
That's Zergle modules for you, yeah?
Yeah, but can you in this picture see the monodromy action?
Well, that's a longer discussion, and yes, I can, but we can talk about that later point.
Okay.
But since the group is acting on the space on the non-equivariant cohomology, you have action of odd variables.
Say that again. Could you repeat what you just said?
The group is acting on the space. Then, therefore, H1 of the group, homology of the group, homology of the group acts on the space.
Correct.
On the cohomology of the
And
space.
homology of G is this exterior algebra.
Correct.
Or it's this Koszul complex, I guess.
Yeah, since you've, the advantage of topology, of course, is when you forget a T action, you've automatically thrown in the Koszul complex by default. Topology does that without having to resolve anything.
Yeah.
Because now you have
But
a free action. You have a free action, right? So.
Yeah. I would like to, maybe sometime later, I would be curious if how in that picture you see this monoger reaction, this R upper check action.
Sure, we could discuss that at a later point. I just wanted to make sure I sort of have a picture in mind of the objects in LM.
Yeah.
Mhm.
And then the objects of LM are like this, but they're also twisted complexes built from such.
Sure. Yeah, the curvature. Yeah. That's interesting.
No. These guys are not curved. You take Bose-Samuelson guys.
Yeah, right.
Yeah, you take Bose-Samuelson guys. You don't really. Whether or not you take cohomology is up to you, but you could just take like chains, cellular chains on such a thing. And I guess we're looking at complexes built from those, like cones, iterated cones built from them.
Yeah,
So a typical object of LM is not just one of these things, but it's some of these things connected by some differentials.
Yeah, I'll have to learn more about it. Yeah, I'm just trying to make sense of it.
Yeah,
Sorry, I don't want to monopolize the whole question and answer thing. Thank you.
Can I fix some? I was confused. You wrote that on LM objects you have R action on the right and R check actions on the left. I thought it would be lambda check actions on the left.
It's R check on the left. So remember, elements of the lambda are not closed. These thetas are homotopies that kill x's, so they die. Lambda, the cohomology of lambda is just one-dimensional. So when we talk about the homotopy category, like LM, when we talk about like closed endomorphisms of an object or whatever, none of them are going to come from thetas because those are just not closed. But they come from. It really is the action of Hochschild cohomology of lambda. So, you should really think of like an object of LM is a complex constructed from pieces that look like Koszul complex, tensor, Zergle bimodule. And so entries of the differential of such an object are like morphisms in the category of Zergle bimodules, but like with coefficients in lambda. And then what you're doing, the R check action is, and this is not my idea, by the way, this is in AMRW and those people, but the idea is you're applying your class in Hochschild cohomology of lambda to the differential. You write your differential as in terms of its components, and then you apply your Hochschild cohomology class to the coefficients.
Can I think about it as you take D square and then it's in the image of K differential, so you expand it in like thetas with some.
You can, yeah, you're right. That's the same thing. Your differential is so. Yeah, it's the same. It's the same thing. So like Y is so this guy YI is a class in HH upper 2. So it accepts 2 inputs. So that the endomorphism that you call YI is really whatever class in HH upper 2 evaluated on delta comma delta. Like, yes, you take D squared and you pair that against your Hochschild cohomology class. I mean, I guess if you want to think of it.
No, I think it's
Sorry,
easier.
I think I'm saying it wrong.
Square, it's in the image of dk, so you can write it as like sum of theta i's with some coefficients.
Yeah, that's this. Yes,
And
that's
the coefficients are the actions of yi, basically.
That's right.
I think so.
Before we stop, Ben Cooper, who I don't think is still here, asked a question on chat, which I figure we might as well answer to get in the video. So he asked whether Jake Rasmussen's differentials in type A extend to this construction as well. Or
absolutely.
When he asked the question, it wasn't clear which construction you were working on at the moment. But
so do Jake's differentials in type A fit into this construction? I presume he's talking about the Wi-Fi category, this curved Hecke category.
I think he asked the question when you were defining LM, but it doesn't matter. I now ask the question for all the for all four.
Oh, for all of them?
Yeah.
So yeah, I would say that so.
And he also asked whether it makes a difference to homology.
Isomorphic homology. That one I don't know how to parse. Possibly what, okay, here's my reinterpretation of Ben Cooper's question. So we have these two categories, BE and FM. They are Koszul dual in some sense. And you can define link homology from either side. And those are supposed to be isomorphic, maybe in some sense. And I think his question might have been, do they remain isomorphic after you take Jake's differentials? That I don't know, but I don't.
But you swap x's and y's, right? I mean, like for unknown.
Yeah,
Either
I mean,
like kill x to the end or you kill y to the end, so it's pretty different.
I mean, I think so.
Matt, may I make a certain suggestion regarding category Y?
Yeah.
Maybe it is equivalent to one of the categories that you presented. I'm just trying to understand what goes on. So in our previous work with Mikhail, we had category to describe triply graded homology. We use category of homotopy category of complexes over the derived category of bimodules.
Yes.
So now let us, on both sides of bimodules, let us throw in a set of n variables y, different variables. So
yeah,
throw in 2n y variables, not just n.
Right.
So now the bottom category becomes derived category of xy bimodules.
So I want to write this because I sometimes have you want it to be derived
bimodules, yes, bimodules, and that will be the bottom category. And on top of it, you want the category of matrix factorizations on top of it, meaning MF of this one, comma the potential xi yi right minus xi yi left. This will be symmetric. Now, if you want to represent, a braid, say some simple braid, then you would pair. So you use Hecke complex, but in addition to the X bimodule, to the X Zergle bimodule, you will tensor it with the virtual bimodule for Y's.
These are the identity. The virtual. Okay.
Virtual crowd, which means you equate left Y's with right Y's according to.
Yes.
Yeah.
And I guess that would be equivalent to what you're doing. So in your construction for Y, you sort of use different Y categories for each permutation. And there is no place for Zergle bimodule for individual Zergle bimodules, if I understand.
Well, I'm a little confused though, because this is a part of the story that always confuses me. So if you're really considering honest matrix factorizations, so this is your potential Z.
Hey guys, this sounds like a long conversation. Let's thank the speaker, and then we'll
Okay.
we'll continue.
All right.